a quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in, let the outside world dissolve, and gently descend into tonight's world. Across decades, a strange idea has moved from philosophy into physics, computer science, and everyday online debate. It is the possibility that what we call reality is not the base layer, but a constructed experience, like a world rendered for a mind. The simulation hypothesis does not claim a single clear scenario. It is a bundle of arguments, clues, and pressures that point in the same direction, along with serious counter-arguments that push back. Some reasons are mathematical, some are technological, some are psychological. Some are about how knowledge works and what any observer can actually measure. In this episode, we will lay out the strongest versions of these arguments, explain why they convince some people, and also show where they may fail. Tonight, we go through 75 best arguments that we live in a simulation. Start with the most careful point. Nobody has direct access to reality, except through experience and measurement. Everything you know about the world arrives as data to a nervous system, and every instrument extends that nervous system with sensors and models. Even before anyone says the word simulation, this creates a gap between the world and the picture of the world. The gap is not a trick, it is a basic fact. You do not see atoms directly. You see tracks in a detector. You do not touch an electromagnetic field directly. You feel forces and infer causes. A simulation claim fits into this gap by saying the picture is not just incomplete. It may be the only layer we ever interact with. One argument begins here. The possibility space is large. There are many ways to produce the stream of experience an observer receives. A universe made of continuous fields is one way. A universe made of discrete updates is another. A universe that is computed is another. Most of the time, we assume the simplest story is that the world is just there as it seems, and our models slowly approach it. But history shows that what seems obvious can be wrong. The earth feels still. The sky feels like a dome. Time feels universal. Then careful measurement breaks the feeling. The simulation hypothesis treats our everyday intuition as one more feeling that could be misleading. A common pushback says this is just skepticism dressed up with computers. But computers matter because they provide a concrete mechanism. In earlier centuries, people could imagine illusions, dreams, or gods. Today, we can imagine a system that generates consistent rules, responds to interventions, and produces shared experiences for many observers at once. We also know such systems can be built in principle because we build smaller versions already. Every modern video game is a tiny case where a world is not a world, but a set of calculations that create an experience. That leads to a first major class of arguments, the argument from technological progression. It says that if civilizations survive long enough, they tend to build better and better simulations. They model weather, then biology, then brains. They build virtual worlds that become more realistic. If there are many advanced civilizations in a larger universe, then the number of simulated observers could outnumber the number of original observers. If you pick a random observer from the total set, you are more likely to be simulated than original. This is sometimes called an observer counting argument. The point is not that we already can simulate a full universe today. The point is that we might be early in a curve. In just a few decades, we went from blocky pixels to realistic faces on screens. We went from simple physics demos to complex fluid simulation. We went from phone calls to global video. We went from handwritten maps to satellites. The curve is not smooth, but the direction is clear. If you extend that direction far enough, you get the ability to simulate a world that includes minds. At that stage, the strongest version of the argument does not require a perfect simulation of the entire cosmos. It only requires a simulation of the local environment needed for the simulated minds. If minds live on a planet, you might simulate the planet in high detail, simulate the nearby sky enough to be convincing, and only compute distant galaxies when someone points a telescope. In computer graphics, this is like level of detail. You render what the player sees. In physics, it resembles how measurement seems to bring a definite outcome into view. This touches a second class of arguments, the argument from apparent economizing in nature. When people look closely at the laws of physics, they see patterns that look like constraints. There are speed limits. There are quantized values. There are uncertainty relations. There are conservation laws. Not everyone agrees these look like computational tricks. Many physicists see them as fundamental structure. But the simulation-minded person says constraints are what you expect in a system that is trying to be stable, consistent, and efficient. Consider the speed of light limit. In our universe, information cannot travel faster than a fixed speed in a vacuum. This is deeply woven into relativity, but it also resembles a maximum update rate for causal influence. In a distributed computation, you cannot send signals instantly across the grid. There is latency. There is a speed limit set by the system. A simulation story can treat the speed of light as that kind of limit. Now consider quantization. Energy comes in packets. Light is made of photons. Electric charge comes in discrete units. The world is not a smooth continuum at every level we measure. Again, this may be just how reality is, but it also matches how digital systems work. A digital image is not infinitely smooth. It has pixels. A digital sound is not infinitely fine. It has samples. A simulation argument says the universe may have a smallest unit of space and time, like pixels and frames. A third class of arguments comes from computation itself. Modern physics can be expressed in mathematical forms that look like information processing. There are equations that predict how a system moves from one state to the next. There are limits on how much information can be stored in a region of space, like the holographic principle. There are ideas in black hole thermodynamics that connect entropy, area, and information in a way that feels like storage capacity. In this view, the universe does not just contain matter and energy. It contains information, and information behaves like a physical thing. When you combine these points, you get a picture. Reality might be an information system. If it is an information system, then a simulation is one kind of information system. The step from information to simulation is not forced, but it becomes easier to imagine. And when imagination meets statistics, the observer counting argument returns. Another argument is more personal. The argument from consciousness being substrate independent. If you believe that a mind is a pattern of information processing, not a magical substance, then it might run on many substrates. It could run on biological neurons. It could run on silicon chips. It could run on something else entirely. If minds can be instantiated in different physical systems, then a simulated mind is not a fake mind. It is a real mind implemented in a different way. This matters because the simulation hypothesis is not about us being holograms with no feelings. It is about our minds being real while the world around us may be generated. A related point is the argument from brain emulation. Researchers already map neural circuits in animals. They simulate small networks. The dream is that someday we will model a whole human brain with enough detail that its behavior matches a living person. Even if that is hard, it is not obviously impossible. If it is possible, then we might build many copies. And if we build many copies, then again, the number of simulated minds could dwarf the originals. Now, a critic will say, this assumes the larger universe has many advanced civilizations, and that they choose to run huge numbers of ancestor simulations. Maybe civilizations usually destroy themselves. Maybe they do not care. Maybe they consider it immoral. Maybe they prefer other kinds of virtual worlds. These are real counter-arguments, and they are part of the standard trilemma people discuss. Still, the simulation argument is not that it is certain. It is that, under some plausible assumptions, it becomes likely. The next group of arguments uses clues from how our physics looks when pushed to extremes. One such clue is the way quantum mechanics forces probabilities into the heart of prediction. At the smallest scales, we do not predict a single outcome. We predict a distribution. When we measure, we get one result. Then the distribution updates. There are many interpretations of this, and physicists disagree about what it means. But to a simulation-minded person, probability and measurement look like a rendering pipeline. Before you look, the system does not spend resources committing to a single detailed state. It keeps a compact description. When you look, it samples an outcome. This is not a proof. It is an analogy. Nature does not owe us analogies that match our computers. Still, the analogy is powerful because it maps onto a real design strategy. Do not compute what no one can observe. Compute what matters for the observers. Another clue is the role of symmetries and invariances. The laws of physics appear the same in many situations. If you rotate your lab, the rules do not change. If you move at constant velocity, the rules do not change. These symmetries make the universe compressible. They mean the laws can be described with short equations rather than endless tables. A simulation argument says, compressibility is what you want if you are writing code for a world. You want simple rules that generate complex behavior. Complexity from simple rules is a major theme in cellular automata and other computational systems. A grid of cells updating by simple local rules can produce patterns that look like life, turbulence, and self-organization. If a simple automaton can generate surprising richness, then a world like ours might be the output of a rule system at a deeper layer. Again, this does not show it is simulated. It shows that simulation is a coherent option. There is also the argument from fine-tuning. The constants of physics seem to sit in a narrow range that allows stable atoms, chemistry, stars, and life. If the constants were slightly different, complex structures might not form. Some people take this as evidence for a multiverse. Some take it as evidence for design. A simulation-minded person can take it as evidence of parameter selection. In a simulation, you choose constants to get the outcomes you want. You might tune a world to produce interesting complexity. However, fine-tuning arguments are tricky. We observe a life-permitting universe because we are here to observe. That is the anthropic principle. Fine-tuning could be selection bias, not design. Still, the simulation idea folds into it naturally. A simulator might run many worlds and keep the interesting ones. At this point, it helps to be specific about what counts as an argument. Many popular claims are weak, like saying the world feels weird, or coincidences happen, or glitches appear in video footage. Those are not strong. The stronger arguments are structural. They rely on math, physics, computation, or probability. But there are also arguments that come from human behavior and social patterns. For example, people build virtual spaces as soon as they can. We build stories, theatre, paintings, films. We build games. We build social media worlds. We build VR. This suggests a desire to create alternate realities is common in intelligent beings. If that desire scales with technology, then advanced beings might create large-scale virtual worlds, not because they must, but because they will want to. Another social argument is that we already outsource memory and decision-making to machines. We let algorithms curate what we see. We let maps tell us where to go. We let recommendation systems shape culture. This is not a simulation of physics, but it is a simulation of social reality. It shows how a layer of computation can become the effective world people live in. If that can happen socially, it could happen physically. Now move to a more technical argument. Limits on computation appear in physics itself. There is a maximum amount of information that can pass through a channel. There are bounds, like the Bekenstein bound, which limits the entropy and thus information content in a region given its energy and size. There is the idea that a black hole is the densest information storage object possible, and its entropy scales with surface area, not volume. This is strange if you imagine information filling space like gas. It is less strange if you imagine information being stored on a boundary, like data on a surface. The holographic idea is not just a metaphor. It shows up in real mathematical dualities, like ADS-CFT, where a theory of gravity in a volume can be equivalent to a theory without gravity on a boundary. The simulation-minded person hears this and thinks, maybe our 3D world is an emergent projection from a deeper description. And a projection is exactly the sort of thing a simulator would generate. But a physicist can respond. Emergent does not mean simulated. A shadow is emergent from an object and a light source, but it is not computed. Still, the fact that deep physics points to information and boundaries keeps the simulation idea in the conversation. Another argument is from digital physics, the idea that the universe at bottom is discrete and computational. Some researchers explore models where space-time is made of nodes and links, like a network. Others explore causal sets where events have an order relation. Others explore loop quantum gravity, where areas and volumes are quantized. None of these are mainstream proofs of simulation, but they show that serious physics can live in discrete frameworks. At this stage, a simulation argument can be framed carefully. If the deepest physics is discrete and rule-based, then there exists a description of our universe as a computation. Whether that computation is being run by someone, or is just the universe doing what it does, is a separate question. The simulation hypothesis adds the extra claim that there is an external hardware, an external context, and perhaps external agents. So the question becomes, do we have any evidence of an external context? This is where many arguments become speculative, but there are a few that at least touch testability. One test idea is to look for artifacts of discretization, like a lattice structure. If space were a grid, maybe high-energy particles would show anisotropies, meaning their behavior would depend slightly on direction relative to the grid. Researchers have looked for such effects. So far, nothing convincing has been found at accessible energies. But the search itself is important. It means simulation can, in principle, have physical signatures. Another idea is to look for limits on resolution. If there is a smallest length scale, there might be noise or deviations from smooth physics at extremely tiny distances. Some quantum gravity approaches predict such effects. Again, nothing decisive has been seen. There is also the argument from computational resource limits. If a simulator has finite resources, then the simulation might sometimes take shortcuts. It might approximate distant regions. It might cull information that is not needed. Some people fantasize about finding such shortcuts, like errors in the background of the cosmos. But a careful response is that a sufficiently advanced simulator could hide artifacts very well. And if the simulator is truly advanced, their computational resources could be enormous. So lack of visible artifacts does not strongly argue against simulation. A different approach is the argument from uncanny effectiveness of mathematics. Why does math, invented in human minds, describe the physical world so well? Some people take this as evidence that reality is mathematical. A simulation story can say, of course, math describes the world, because the world is generated by rules, and rules are math. But there are other explanations too. We use math that fits the world because it works. We discard the math that does not. Still, the fit is striking. Another argument is from algorithmic compressibility. If the universe is generated by short rules, then the patterns we see should be compressible. Many physical laws are indeed simple. A simulation-minded person says that is what you expect. A critic says that is what you expect in any lawful universe. So it is not decisive. Now consider the argument from apparent randomness. In physics, randomness shows up in quantum outcomes. If quantum randomness is truly random, then it is not the output of a deterministic computation, unless the computation includes a random source. But in a simulation, randomness can be produced by pseudo-random generators, which are deterministic but unpredictable without the seed. A simulation argument says quantum randomness might be pseudo-random, seeded outside the simulation. That idea leads to a test. If quantum randomness is pseudo-random, maybe it has patterns. But detecting such patterns would be extremely difficult. And if the simulator is competent, they would use a generator that passes all feasible tests. Another personal argument is the feeling of being an observer. You do not experience the full world. You experience a narrow stream, a few senses, a few memories, a viewpoint. In a video game, the player also has a viewpoint. The game renders what the player can see. The simulation argument says that the structure of experience, being centered on observers, is what you would expect in a simulation. But again, it might also be what you expect in any universe where minds evolved. The next cluster of arguments involves time. In our physics, time is strange. In relativity, there is no universal now. Different observers slice space-time differently. In some approaches to quantum gravity, time might be emergent, not fundamental. If time is emergent, then it might be like the frame rate in a simulation. an ordering of updates rather than an independent flowing substance. The simulation argument says our sense of time could be a byproduct of the update structure. Yet many philosophers will say emergent time is not evidence of simulation. It is evidence that our best theory does not treat time as simple. Still, if time is emergent, then the idea of a computed history becomes less strange. At this point, we can start to build a more systematic set of arguments, still in continuous narration, but clearly separated by transitions. We can ask, what would make simulation more likely than not? One major lever is the scale of possible simulated minds. If you accept that minds can be emulated, then in principle, a single advanced civilization could run many copies. The ratio could be enormous. Even if only a fraction of civilizations do this, the number could still dominate. But you might reject emulation. You might believe consciousness requires a special biological substance or a special quantum effect. If so, simulation becomes less likely. So a key argument for simulation is also a key argument for computational theories of mind. Another lever is the base reality. If base reality is infinite or has endless resources, then it could run endless simulations. If base reality is finite, it still might run many. We have no clear knowledge of base reality by definition. Now, a skeptical response says, all of this is just possibility. It is not evidence. But probability arguments often work with possibility when direct evidence is inaccessible. The question becomes which assumptions are reasonable. From here, we can expand into many specific arguments that people treat as signs of simulation. Some are stronger, some weaker, but the goal is to present the best versions. One argument says that our universe appears finely tuned not just for life, but for computation. The constants allow stable atoms and chemistry, but also allow information processing, stable memory, and error correction. Life itself is information processing. If the universe is designed for computation, that fits a simulator story. Another argument points to the fact that physical law seems local. The rules at a point depend on nearby conditions. Local update rules are exactly how you build large simulations efficiently. A global rule that depends on the whole universe is harder. Locality is a major design principle in computing, but locality could also be fundamental. It might be required for causality. It might be required for any stable universe. So again, it is suggestive, not decisive. Another argument is that the universe has a limited speed of information, which also makes local updates possible. If everything influenced everything instantly, you would not have a simple simulation. So the speed limit fits. There is also the argument from the cosmic horizon. We can only see a finite region of the universe, limited by the age of the universe and the speed of light. We cannot see beyond. In a simulation, you might only render what is within the accessible region for the observers. The horizon could be a rendering boundary, but in physics, horizons are natural in expanding universes and relativity. They may not imply simulation. At this stage, we have laid down the core scaffolding. Next, we will push through many more arguments, including ones about quantum measurement, information bounds, the structure of space, the stability of physical law, the psychological appeal of the hypothesis, and the hardest counter-arguments that keep this from being a simple conclusion. A careful way to proceed is to treat each argument as a pressure on the default assumption. The default assumption is simple. The world exists as it appears, in a single physical layer, and we are part of it. Each simulation argument says there is an alternative that is not only possible, but in some ways natural. When enough independent pressures point the same way, people start to take the alternative seriously. One pressure is that intelligence tends to create models. A model is a simplified world. A model can be run, rewound, and tested. A species that becomes technologically advanced will not stop modeling. It will model itself. That is not science fiction. It is already a goal in neuroscience and AI research. A perfect self-model would include a model of the world and the agents in it. Now imagine a later stage, when the models are not just tools, but places. In our own time, people already spend hours a day in digital spaces. They work there, socialize there, and build identity there. This is a hint about future preferences. If future beings can create worlds that are more immersive than any game we know, many will choose to live inside them for long periods. The difference between base reality and virtual reality could blur, not because of a philosophical trick, but because daily life shifts. This leads to a version of the argument that does not rely on ancestor simulations at all. It says, if virtual worlds become common, then most conscious time may be spent inside virtual worlds. Even if the number of individuals in base reality stays larger, the total hours of experience could be dominated by simulated settings. If you condition on being an experiencing observer at a random moment, you might be more likely to be in a simulated environment. A critic can reply that this still assumes minds can be hosted in a simulation. That is a deep question. But the simulation hypothesis often assumes a naturalist view of mind, that a mind is what a system does, not what it is made of. If that view is correct, then simulation becomes much more plausible. A second pressure comes from how strong the universe is at producing structure from simple law. Consider how a few basic forces and a few parameters give rise to stars, chemistry, planets, weather, and biological evolution. Complexity in our universe is not hand-built. It emerges. A simulation designer could take advantage of this. Instead of coding every detail, they could set initial conditions and let the world run. If you were building a simulation for research or entertainment, this is exactly what you would want. You would want an engine that produces rich outcomes without constant intervention. You would want stable rules that allow unpredictability, like a game with emergent gameplay. Our universe looks like such an engine. From there, a third pressure is the idea of layers. In software, complex systems are built in layers: hardware, firmware, operating systems, applications. Each layer treats the lower layer as a set of services. It does not need to know the deeper details. In physics, we also have layers: thermodynamics, chemistry, biology, psychology. Each layer can be described by its own rules. A simulation argument says this layered structure resembles a computational stack. Of course, layered description is also just a feature of reality and of human knowledge, but the resemblance remains. When you can compress a layer into a simple set of effective laws, it feels like an interface. Now consider a pressure that comes from epistemology, from what it means to know something. Suppose you are inside a simulation. Your observations are part of the simulation. Your instruments are part of it. You cannot step outside to compare. This means that most direct tests will fail by design, but it also means something else. The simulation hypothesis is not easily disprovable, and that is a reason many scientists treat it cautiously. Yet not being easily disprovable is not the same as being meaningless. Many claims about the deep structure of reality are hard to test. We still explore them because they organize our thinking and sometimes generate indirect predictions. A fourth pressure comes from a specific, probabilistic argument called self-locating uncertainty. Even if you accept only a small chance that advanced civilizations run simulations, you can still assign non-trivial probability to being in one if the number of simulations is huge. This is similar to reasoning about the chance you are in a rare group when the group is massive. But self-locating reasoning is controversial. It depends on how you count observers, how you define a reference class, and whether you treat copies as separate. Critics argue that these choices are arbitrary. The simulation argument is only as strong as the observer measure behind it. Still, it is not arbitrary in the everyday sense. If you had to bet, and if you believe there are many more simulated minds than base minds, then it is rational to place a higher probability on being simulated. That is the core. Now shift to an argument that tries to link simulation to actual patterns in physics. People often mention that space-time might be discrete. If it is discrete, then at the smallest scale, there is a grid or network. A digital system updates in steps. That sounds like a simulation, but there is a subtle point. A universe can be discrete without being simulated. Discreteness does not automatically imply an external computer. It implies that the fundamental description has countable elements. Still, if the fundamental description is countable and update-based, it becomes easier to imagine that it could be implemented as a computation. And once you imagine implementation, you imagine implementers. Another argument from physics is that the laws of nature have a certain kind of elegance. They are not just random constraints. They have symmetry. They have simple forms. Many people feel that the universe looks like a well-written program. Again, that is aesthetic. But it is a genuine impression, and it drives some of the interest. Now consider a pressure from the history of science. Again and again, we have discovered that the world is not how it appears. Solid matter is mostly empty space. Time is relative. The same event can have different time order for different observers, depending on frame. Particles can be entangled so that measurement outcomes correlate across distance. The universe can be expanding. These are not small corrections. They are deep shifts. From that pattern, one can argue that the next deep shift might be about the nature of reality itself. The simulation hypothesis is one candidate shift. It says the next step is not just new laws inside the universe, but a new understanding of what the universe is. Another pressure is the role of observers in quantum theory. Some interpretations make the observer central, or at least make measurement central. It feels strange that the act of measurement is so important in the math. In everyday life, measurement should be passive. In quantum mechanics, measurement is not passive. It changes the state. A simulation analogy says, that is what happens when you query a system. You force it to produce an output. Before the query, it may not have stored the output. It may have stored a compact state. When you ask, it produces a value and then updates. This is exactly how many computations behave. This is not a proof. It is a way of making a weird feature of physics feel less mysterious. Many physicists reject the rendering analogy. Still, it is one of the most cited reasons people think simulation is plausible. Another argument, closely related, is the idea of level of detail. In computer graphics, distant objects are rendered with less detail than nearby objects. The player experiences a coherent world, but the engine uses shortcuts. In a simulation of a universe, you could do something similar. You could compute the local environment at high fidelity and keep distant regions as a compressed description. This idea becomes tempting when you think about how little of the universe is actually observed. Most of the cosmos is beyond our reach. Even within reach, most of it is never measured in detail. A simulation could store the unobserved parts as statistical distributions and only resolve detail when an observation forces it. A skeptic will say, physics already uses distributions because our knowledge is limited, not because reality is. That is correct. But quantum mechanics is strange, because the distributions do not obviously sit on top of hidden variables. They appear to be the best possible description. This keeps the rendering analogy alive. Now consider the argument from computational irreducibility, a term used in discussions of complex systems. Some systems cannot be predicted except by running them step by step. If the universe contains such systems, then in a sense the universe is doing computation just by existing. It is running its own update rules. From there, some people say that a simulation is just one way of implementing those update rules. If the update rules can exist as mathematics, then they can be instantiated on hardware. That leads to a bigger metaphysical claim. Perhaps all consistent mathematical structures exist. If so, then our universe could be one such structure. In that view, being in a simulation is not special. It is just being in a mathematically defined world. The word simulation becomes a metaphor for mathematical existence. But many people use simulation in a more concrete sense. An external civilization runs our world as software on a machine, so we should keep the discussion grounded. Now, we can start to walk through a set of arguments that people often count as the best, each one adding a distinct angle. One is the argument from the rapid growth of compute. Over the last century, computation has exploded. Even if current trends slow, the long-term trajectory of engineering is to produce more compute per unit of resource, and to use that compute to model and control environments. If this trend continues for thousands or millions of years, the scale of computation available to an advanced civilization could be hard for us to grasp. Another is the argument from increasing fidelity. Simulations today are crude compared to reality, but the gap has shrunk dramatically. Consider faces in films, voice synthesis, and real-time physics. These are still imperfect, but the direction is toward convincing realism. If the gap can become small enough, then a simulated world could be indistinguishable from base reality for the beings inside. A critic will reply, "You can fake surfaces, but you cannot fake the deep structure of physics. That is not certain." A simulator could simulate deep structure if they have the resources, or simulate enough of it to maintain consistency. Another argument is from compression again, but now tied to the fact that the universe seems to have a finite information content within any bounded region. If the state of a region can be described with a finite number of bits, then the region is representable in a finite memory. That makes simulation at least conceptually possible. Another argument is from the way physical law seems to be expressible as computation. Differential equations can be seen as continuous computations. Quantum evolution can be seen as linear transformations on a state vector. Statistical mechanics can be seen as counting microstates. In every case, the language of physics overlaps with the language of information processing. A critic says, overlap of language is not identity, but overlap can still indicate something real. Another argument is from the existence of universal approximators in computation. In principle, a universal computer can simulate any other computable process. If physics is computable, then it can be simulated by a sufficiently powerful universal computer. This is a bridge from computability to simulation. Now, the counter-argument. We do not know physics is computable. The continuum might contain non-computable real numbers, but we have never measured an exact non-computable number. All measurements are finite. Another argument is from the role of initial conditions. Many systems in physics are sensitive to initial conditions. Tiny differences can lead to large changes over time. In computation, initial seeds can produce very different outcomes. A simulation designer might choose initial conditions carefully to get desired results. Our universe appears to have started in a special, low-entropy state. That specialness is sometimes treated as evidence of selection. Now, a critic says, the low-entropy beginning is a deep puzzle, but simulation is not the only explanation. It could be a law or a boundary condition. Another argument is from the concept of algorithmic probability. If you imagine all possible programs generating universes, then simpler programs are more likely under certain priors, because there are fewer bits. If our universe is describable by a relatively simple program, then it would be relatively likely in that space. This is abstract, but it links to the feeling of elegance in physical law. Now, an argument from mind and dreams. In your own experience, you already know what it is like to inhabit a world that is generated by a mind. In dreams, you can see, hear, and feel in a world that is not physically real in the usual sense. Dreams are not stable like waking life, but they prove that rich experience can be generated without a corresponding external world. This does not prove simulation, because dreams are produced by a brain in a physical world. Still, it makes the idea psychologically less impossible. Now, an argument from shared consistency. If we were each in private dreams, the world would not be consistent between us. But our world is consistent. That suggests a shared generator. A simulation provides a shared generator. But base reality is also a shared generator. So again, this is not evidence, only coherence. Another argument is from the mathematical structure of space. Space can be described by geometry. Geometry can be encoded. In a simulation, you can encode geometry as data structures. The fact that our world is so geometrically regular is part of why simulation feels plausible. Now, another argument is that physical law may be optimized for stability. Many stable systems in computing rely on error correction and redundancy. In physics, stable atoms exist because of quantum rules. Stable stars exist because of balance between gravity and pressure. Stable orbits exist. Stable chemistry exists. This stability supports long-term observers. A simulation designer would want stability. But again, stability might just be required for any universe with observers. At this point, it is useful to bring in the idea of selection again. If many universes exist, or many simulations exist, then only those with stability and learnable law produce observers who ask these questions. So the fact that we see a stable, learnable universe is expected under many frameworks. Now keep going with more distinct arguments. One is the argument from the relativity of scale. Human beings live at a middle scale. At our scale, we see classical objects. At smaller scales, quantum behavior appears. At larger scales, relativity and cosmology appear. It is almost as if the world is designed to be navigable at our scale while hiding complexity at extremes. This is not a scientific argument, but it is a narrative one. It suggests an interface tuned for human-like agents. Another is the argument from computational universality in simple systems. Even very simple rule systems can perform universal computation. If that is true, then a simple physical substrate could in principle compute anything, including complex worlds. This supports the idea that a deeper layer could generate our world. Now, another is the argument from the nature of physical constants being dimensionless. Many of the most meaningful constants are dimensionless ratios. They feel like parameters in code, not like arbitrary human units. This makes them feel like chosen settings. Now, a critic says, dimensionless constants are meaningful because they do not depend on units. That is just good physics. Still, seeing the universe as a parameterized system makes simulation intuitive. Now we should shift to the arguments that try to extract hints from the fact that our physics is quantum, and quantum systems are naturally simulated by quantum computers. A classical computer struggles to simulate large quantum systems because the state space grows exponentially. But a quantum computer can simulate quantum systems more naturally. If an advanced civilization uses quantum computation, then simulating a quantum universe becomes more feasible. So one of the best arguments is the fact that our universe is quantum might make it easier, not harder, to simulate at high fidelity if the simulator has quantum hardware. The counter-argument is, if the simulator uses quantum hardware, they are essentially building a universe-like substrate. At that point, the line between simulation and base reality blurs. Now, another argument is about the speed of light again, but framed as a bandwidth cap. If information cannot travel faster than a certain speed, that limits how quickly different regions can coordinate. In a simulation, this could be an intentional cap to keep the computation local and scalable. Now, a skeptic says, this is reading design into a law. Now, a different argument is the one that comes from the possibility of shortcuts in computation for physical processes. We do not know the computational complexity of simulating the universe from the outside. It might be far less than we think if there are deep compressions in the laws. So, to someone who believes in deep compressibility, the resource argument against simulation weakens. Now, to stay honest, we should include again that all of this could be true even in base reality. Simulation remains a metaphysical layer. The draft will continue, and it will also include the practical conclusion that, even if simulation is possible or likely, the best approach for a human being is to treat the world as real in the moral and practical sense, because experience, relationships, and consequences operate inside the rules we live under. To keep building the set of best arguments, we can now move into a series of claims that are often discussed in more technical circles, but that can be explained plainly. One claim is that the universe seems to have a maximum information density. If you try to pack too much energy into a region, it becomes a black hole. A black hole then has an entropy proportional to the area of its event horizon. That is a strange relationship. It suggests that the information describing the interior might be encoded on the surface. In computation, surface encoding is normal. You store data in memory, and memory has a capacity. If you imagine space as having a capacity and that capacity scaling with area, you start to picture space-time as a kind of storage device. Another claim is that many physical processes look like optimization. Light follows a path that minimizes travel time in a simplified view. Classical mechanics can be expressed with action principles, where the path taken extremizes an action. In computation, optimization is everywhere. A simulation can find solutions by optimizing. But in physics, these principles can be derived from deeper equations. So the optimization feel may be a mathematical trick, not design. Still, it adds to the intuition that the universe is rule-based in a way that resembles algorithmic selection. Another claim is that physical laws are the same everywhere we can see. When we look at light from far galaxies, we see the same atomic spectral lines. That uniformity is a constraint. In a simulation, uniformity is the default, because one engine runs everywhere. In base reality, uniformity could also be the default, but uniformity means the world is governed by a small set of rules, not a patchwork. Another claim is that the universe is unusually transparent to analysis. Many chaotic systems exist, but the universe also contains many systems we can understand with compact models. That includes planetary motion, fluid behavior and approximations, electromagnetism, and more. If the world were too messy, no science would be possible. The simulation story can say the world is set up to be learnable, but the anthropic story says, of course it is learnable, because only in a learnable world do you get beings who build science. Now consider a claim about the relationship between observation and reality. In ordinary life, you assume that objects have definite properties even when nobody looks. But in quantum mechanics, that assumption is hard to maintain. Many experiments suggest that certain properties do not have definite values until measurement, at least not in the classical sense. If you take the strongest version of that idea, then unobserved reality is not fully determined. It is a set of possibilities. When you measure, you obtain one outcome. In a simulation, this is natural. You store probability distributions. You sample when needed. Again, this could be an interpretation error, but it is one of the most persistent pieces of the simulation intuition. Another claim is that physics appears to have a built-in firewall between what you can know and what would let you exploit the system. You cannot use entanglement to send signals faster than light. You cannot break conservation laws. You cannot extract unlimited energy. You cannot measure without disturbance. These restrictions protect causality and prevent paradox. In software, you build restrictions to prevent exploitation. If you want a stable world, you prevent hacks. But a critic can reply, physics is not preventing hacks. It is just consistent. The analogy is playful. Still, the pattern is there. The world is stable against many forms of exploitation. Now consider a different kind of argument. The argument from priors and humility. If you are honest, you do not know why there is a universe. You do not know why it has these laws. You do not know why it allows conscious experience. Given such ignorance, it can be rational to assign some probability to strange hypotheses, including simulation. This is not an argument that simulation is likely. It is an argument that it is not crazy. Now consider another, the argument from the future of AI. If we build artificial general intelligence, and if it becomes capable of scientific discovery and engineering at a superhuman level, then it may accelerate our ability to simulate reality. It may also accelerate our ability to build worlds that contain agents. That means the simulation scenario could arrive sooner than we think, at least in partial form. If this is true, then simulation becomes not a distant speculative idea, but a likely future technology. And if it is likely in our future, it might be likely elsewhere. Now, we can include an argument from replication. Once you can run a mind on hardware, copying becomes cheap. A biological human takes decades to grow. A software mind could be copied in seconds. If a civilization makes software minds, then the population can explode in number. That makes simulated observers dominate by sheer count. Now consider the counter-argument. Perhaps software minds are rare, because consciousness does not arise from computation alone. Or perhaps copying minds is restricted legally or morally. Now consider another claim. The argument from observational selection again, but framed as a bet. If you had to bet on what kind of world a typical observer inhabits, and you think advanced civilizations exist, then a world generated by computation might be common. It would be like betting that a typical written story is in a book, not carved into stone. The medium that is easier to produce dominates by volume. Now consider another claim about the limits of our own measurement. Our most precise measurements still have noise. There are fundamental uncertainties. There are limits imposed by quantum effects. There are limits imposed by the speed of light. There are limits imposed by thermal fluctuations. In a simulation, noise can come from finite precision, but in base reality, noise is also natural. The argument is not that noise proves simulation. It is that we never observe the infinitely precise continuum. We always observe finite data. That fits a digital-like world. Now consider the argument from the possibility of external resets. If this were a simulation, the simulator could reset state. They could roll back. They could branch worlds. We do not observe resets directly, but we might not be able to. If your memory is part of the simulation, a reset would also reset you. This makes the simulation hypothesis hard to test, but it also creates a possible explanation for why the world seems consistent and stable. Any glitches could be corrected outside our awareness. Now, be careful. This quickly becomes unfalsifiable, so it is a weak scientific argument, but it is part of the space. Now consider the argument from the observed effectiveness of discrete models. Even if reality is continuous, we model it discretely and get extremely accurate predictions. Weather models, fluid models, and quantum chemistry all use discrete computation. The fact that discrete computation can approximate reality so well makes it easier to imagine that reality itself is discretely computable. A critic says, approximations can be good even when the target is continuous. That is true. Still, the success of computation in describing nature gives the simulation idea oxygen. Now consider the argument from game theory and incentives. If a civilization can run simulations of possible futures, it gains power. It can plan, avoid risks, and optimize. That gives an incentive to build ever more detailed simulations. Over time, the simulations could include agents and societies. Some of those agents might be conscious, so simulation might be an instrument of survival, not just curiosity. Now, another claim is that if simulations are used for planning, there may be many of them. You might run many variations to see which outcomes occur. That multiplies observer count. Now consider a counter-argument. Planners might run shallow simulations without conscious agents. They might simulate only high-level variables. But if consciousness emerges from complex information processing, then even a planning simulation might accidentally contain conscious sub-processes, depending on how detailed it is. Now consider a claim about the beauty of physics. Many scientists talk about beauty as a guide. This is subjective, but it has a track record. If base reality were random, beauty would not be a guide. In a simulation, the rules may be chosen to be elegant. Again, this is aesthetic. Now consider a claim about causality and computation. The universe appears to be causal and local. Computation is also causal and local in many models. This structural alignment makes it easy to map one onto the other. Now consider one of the hardest objections. If we are in a simulation, why do we see such an immense universe beyond our daily needs? Why simulate billions of galaxies? A reply is that you do not have to simulate them at full detail. You can simulate a consistent dataset and generate detail only when observed. Another reply is that the simulator might not care about efficiency the way we do. Another is that the simulation might be for reasons we cannot guess. A critic says, these replies are too flexible. This is fair. So the honest position is that the simulation hypothesis remains unproven. Yet the purpose of this episode is not to prove it. It is to lay out the best arguments and their limits, so the listener understands why this idea has persisted. Next, we will continue toward a full set of 75 by expanding the discussion of quantum information, the measurement problem, the observer counting logic, and the strongest philosophical critiques. Begin with quantum information because it is one of the cleanest bridges between physics and computation. In modern physics, information is not just a metaphor. It is tied to entropy, and entropy is tied to energy and temperature. When you learn something about a system, you reduce your uncertainty. That reduction has a physical shadow. In some settings, it has a cost. The fact that information and physics are coupled suggests that the universe might be described as an information process. If the universe is an information process, then computation becomes a natural language for it. And if computation is a natural language for it, then simulation is not an alien idea. It is a familiar implementation. Now move to a specific point. Quantum systems can be seen as storing information in superposition. A quantum bit can represent more than a single classical state in a certain sense, and the evolution of a quantum system is a unitary transformation, like a computation operating on a state vector. This makes some people think the universe is itself a quantum computer, not a computer sitting in a room, but a system that evolves like a computation. If that view is correct, then the question becomes, is this quantum computation self-contained, or is it being hosted? That question may be unanswerable, but it is still one of the best arguments for why simulation belongs in serious conversation. It is because the universe already behaves in ways that resemble computational state evolution. Now move to the measurement problem, again, but with clarity. Quantum theory gives you a wave function, or state vector. It evolves smoothly according to an equation. But when you measure, you do not observe a smooth blend of outcomes. You observe one outcome. Different interpretations handle this in different ways. Some say the wave function is real and branches. Some say it collapses. Some say the wave function is just a tool for predicting probabilities. There is no consensus. The simulation intuition enters here because the simplest experience inside a simulation is this: the world is computed as needed. When you ask for an output, you get one. You do not see all possibilities at once. Again, this is not a proof, but the structure of the measurement problem lines up with the structure of query-based computation. Now consider the observer counting logic again, but in a more grounded way. Suppose there is a base world with 1 billion observers. Suppose there are simulations that contain 1 trillion observers. Even if the chance that such simulations exist is modest, the conditional chance that you are in one could become large, depending on how you handle self-locating uncertainty. This is the central engine of the simulation argument. It is not physics. It is probability. Critics attack it by attacking the reference class, which observers count as like you. Do you count all minds? Only human-like minds? Only minds with your memories? Do you count copies as separate? These are hard questions. They show that the argument depends on how you define typicality. But typicality is a common tool in cosmology too, where we talk about being a typical observer. Now consider another strong critique. If simulations exist, they may be very different from our world. A civilization might not simulate a universe like ours. They might simulate environments tuned for their own biology or for their own research interests. They might create abstract worlds. They might create worlds with different physics. If that is true, then even if simulations are common, worlds like ours might not be common. So the mere existence of simulations does not guarantee we are in one. A reply is that if you can simulate many worlds, you might simulate many kinds, including ones like yours, and especially if you run ancestor studies. Now, another critique is about the cost of simulating observers with internal complexity. A mind like ours has an enormous internal state. Simulating it at the level needed for consciousness might be costly. If the simulator wants to maximize the number of observers, they might run simpler minds, not human-level minds. If simpler minds dominate, then a typical observer might not be like us. That would weaken the argument that we are typical in the simulation population. But it is also possible that human-level minds are cheap relative to the simulator's resources. We do not know. Now consider one more argument that is often cited as among the best, even if it is philosophical: the argument from underdetermination. For almost any set of observations, there can be multiple underlying realities that produce them. You can imagine base reality producing your data. You can imagine a simulation producing your data. You can imagine a dream producing your data, though that tends to break consistency. Because the data underdetermines the ontology, our confidence in a single ontology should be humble. This humility pushes some people towards simulation as a live option. Now, another point is that science already uses the idea of models that are not literally real, but that predict reality. We use fields, wave functions, and space-time diagrams. Some of these may be real, some may be tools. The line between model and reality is not always sharp. The simulation hypothesis says, perhaps the model-like description is closer to the truth than we think. Perhaps reality is, at bottom, a set of rules generating data. Now we should also include a plain statement of the most important practical counterpoint. Even if the simulation hypothesis is true, we still live under the internal laws. We still feel pain and joy. We still owe each other care. We still build meaning inside the world we experience. In that sense, simulation is not an escape hatch. It is a question about the deepest layer, not a license to treat life as a game. As AI systems improve, they may be able to generate convincing worlds at scale. They may generate characters who speak, react, learn, and perhaps even suffer. The moment we see convincing digital agents, the simulation hypothesis becomes less abstract, because we will have built a small version of it ourselves. And if we build such systems, we will face a mirror. We will have to ask whether the agents inside our own worlds are only images, or whether they are minds. We will have to ask what we owe them. And we will have to admit that, from their point of view, the world they know is the world that exists. The deeper layer does not make their lives less real. Now we can extend the list beyond 50. Argument 51 is about error correction. In quantum physics, error correction codes show that you can protect information even when noise is everywhere. Some researchers have noticed that parts of gravity and space-time math look similar to error correction. The simulation-friendly idea is that the universe protects its state, the way a computer protects data. The objection is that nature can have error correction without being a simulation. It can be a deep principle, not a design choice. Argument 52 is about compression. When a system has strong patterns, you can compress it. Physics is full of patterns. Laws compress huge amounts of data into short equations. A simulation would also rely on compression, because storing every detail separately would be expensive. The objection is that compression is also what we expect if the universe is lawful. Laws do not imply code. Argument 53 is about finite information. Many physicists think there is a limit to how much information can fit inside a region of space. The holographic principle is one version of this idea. A hard information limit feels like a memory limit. The objection is that an information bound could be a property of reality itself. Argument 54 is about discrete measurements. At very small scales, energy levels come in steps. Charge comes in units. Angular momentum comes in units. Discrete steps fit well with a digital picture. The objection is that quantum discreteness is not the same as a pixel grid. Argument 55 is about speed limits. The speed of light is a strict limit for signals. In computing, there are also limits on signal propagation and update speed. A simulation could have a maximum update rate. The objection is that a speed limit can come from geometry, not computation. Argument 56 is about randomness. Quantum outcomes look random. Simulations often use pseudo-random number generators, so some people ask if quantum randomness is algorithmic. The objection is that quantum randomness might be truly random. Also, a simulator could use real randomness too. Argument 57 is about rule tuning. The constants of nature look finely tuned for complex structures. Some people treat this as evidence of design. A simulation could tune constants to get stable chemistry and long-lived stars. The objection is that fine-tuning has other explanations, like many worlds or selection effects. Argument 58 is about sandboxing. In computer security, you sandbox processes so they cannot access the host system. Our universe feels sandboxed. We do not see the outside layer. The objection is that this is just how physics is. A closed universe is not the same as a sandbox. Argument 59 is about computational irreducibility. Some processes cannot be shortcut. You must run them step by step to see what happens. If the universe is doing step-by-step updates, that is compatible with being computed. The objection is that irreducibility can happen in a non-simulated universe too. Argument 60 is about render distance as a test idea. If details are generated only when needed, then extreme observations might show limits, like missing detail beyond a scale. The problem is that physics has been tested very far, and it holds up. So this is more of a thought than evidence. Argument 61 is about energy as a budget. In a simulation, computation costs resources. In physics, changing information has energy costs, like Landauer's principle. This makes some people think the world is paying a compute bill. The objection is that Landauer applies to physical computers inside physics. It does not prove physics is itself a computer. Argument 62 is about reversibility. Fundamental physics is often reversible in time at the microscopic level. Many computations are also reversible in principle, so the mathematical structure matches. The objection is that reversibility is a general symmetry idea, not a simulation clue. Argument 63 is about the universality of math. Mathematics describes the universe with strange accuracy. If the universe is generated by rules, math is the natural description of rules. The objection is that math could describe reality because we built math to match patterns we see. Argument 64 is about limits on observation. There are strict limits on measuring certain pairs of properties, like position and momentum. In a simulated world, limits can be built in to prevent access to the underlying state. The objection is that uncertainty is a core quantum feature, not a privacy setting. Argument 65 is about the no free lunch of detail. To get more detail, you must spend more energy, time, or experimental effort. In a simulation, high detail could require more computation. The objection is that experiments are costly in any universe. Argument 66 is about glitch stories, handled carefully. People report odd coincidences or matrix moments. These are weak evidence because human memory is biased and pattern-hungry. Still, the fact that many people reach for the same metaphor can show how natural the simulation idea feels. Argument 67 is about AI world building. We are already building systems that generate images, voices, and interactive scenes. As this improves, it becomes easier to imagine full worlds. The objection is that imagining is not proving, but it increases plausibility. Argument 68 is about economic incentives. If simulations can produce knowledge, art, entertainment, or training, there will be incentives to run them. That makes many simulations more believable. The objection is that incentives do not guarantee capability, and capability does not guarantee that people simulate conscious lives. Argument 69 is about ancestor curiosity. If you could simulate your past with high detail, you might do it to study history. That would create worlds with humans like us. The objection is that detailed ancestor sims might be unnecessary or ethically rejected. Argument 70 is about nested worlds. If simulated worlds can create their own simulations, There could be many layers. This makes it hard to say what is base. The objection is that nesting might be limited by resources, and each layer might be less detailed. Argument 71 is about normalization. If you live inside a simulation, the world will feel normal. Your entire life is inside it. This means the absence of obvious weirdness does not count strongly against simulation. The objection is that this makes the idea hard to falsify. Argument 72 is about why these laws. The laws of physics are strangely simple and consistent. A simulation might pick laws that are stable, elegant, and computable. The objection is that we do not know what alternative laws would look like, and simplicity can be a deep truth. Argument 73 is about observability and API thinking. We interact with reality through measurements. Measurements are like queries. A simulation could expose an interface, not the raw state. The objection is that measurement is just interaction. Calling it an API is metaphor. Argument 74 is about limits of prediction. Even with good laws, complex systems are hard to predict. Weather, brains, and markets are examples. A simulation could still exist while staying unpredictable for inside observers. The objection is that unpredictability is expected from chaos and complexity. Argument 75 is about the moral mirror. If we can build worlds with agents that feel real, we will face the same question we ask about ourselves. Are they just code, or are they minds? This argument does not prove we are simulated, but it shows the question is not science fiction. It is a near-future ethical problem. So the strongest arguments for a simulated reality do not end with a simple answer. They end with a shift in perspective. They remind us that reality is what holds stable under inquiry, that minds can be patterns, and that the rules we live under are consistent enough to let us build science, technology, and meaning. Whether the deepest layer is base matter or hosted computation, we still wake up inside this world, and we still face the same responsibilities to one another. This was a quiet archive story, where the story ends, sleep begins.